Today we're going to continue practicing solving systems of linear equations graphically. And we're going to add some new terms to how we can describe systems of linear equations. So let's get started. When we're looking at a system of two linear equations, we're looking at how two lines interact with each other, or how they're related to each other. And they're going to be related in one of three ways. As we saw in our previous lesson, we can graph these two equations, and our two lines are going to cross in one location. And where these two lines cross or intersect, that is the solution to that system. And with two linear equations, they're only going to cross once. It's not like one line is somehow going to bend around and cross the other line again. This point of intersect is the one ordered pair, the one point that both lines have in common. So this is one of three ways that two linear equations can be related to each other. A second is if the two lines are parallel to each other. These two lines are parallel. They have the same slope, so they're changing at the same rate, but they cross the y-axis at a different location. So parallel lines have the same slope, but a different y-intercept. So in this case, there will be no solution. These lines will never cross each other. They will never intersect on our two-dimensional graph. And then with our third relationship, here we have one line on top of the other. This may be hard to see. We've got the blue line slightly shorter, so that you can see the red arrow pointing above it. But the two equations here produce the same line graphically. So every point on one line is also on the other line. So they have infinite number of points in common. If a point's on one line, it's going to be on the other line. So in this case, the solution to this system of two linear equations is infinitely many solutions. So again, those three ways that two lines can be related, well, they can cross at one point, and they have one solution. They can be parallel lines that have different y-intercepts, and these two lines will never intersect, so they have no solution. Or they can represent the same line, and in this case, they'll have infinitely many solutions. Let's look at a few more terms. So if there's one solution or infinitely many solutions, that means there is a solution to this system of linear equations. And we say that that system is consistent. A consistent system has a solution. In this case, it may be one solution for two linear equations, or it may be infinitely many solutions. Well, the opposite of consistent is inconsistent. So an inconsistent system has no solution, which is what we saw with parallel lines. Looking at a few more terms to describe systems of linear equations, when we have infinitely many solutions, well, this means that these two equations represent the same line. So one line is a multiple of the other. You can take one of those lines, multiply it by a constant, and get the other line. So the lines are dependent on each other. So a dependent system has infinitely many solutions. And so if we have a dependent system, we also have the opposite, the independent system. And with an independent system, each equation in the system represents a distinct line. So we're either going to have one solution, where the two lines cross, or no solution. And that occurs when the two lines are parallel and cross the y-axis at a different location. So we can summarize these terms. If the system has a solution, which we see with the one solution example where the lines cross at one location, or The infinitely many solution example, where the system represents the same line, well, that is consistent. Consistent systems have solutions. With parallel lines, we did not have a solution, so that was inconsistent. Now, if our equations are dependent on each other, meaning they describe the same set of points, well, this is a dependent system. And if that's not the case, then it's an independent system. Now let's practice solving some systems of equations by graphing. And then we're going to classify the systems as either consistent or inconsistent, and as either dependent or independent. Now previously, when we were asked to solve systems of equations by graphing, the equations were in slope-intercept form. So we were able to pull information from the equation, namely the slope and the y-intercept, to graph it. Today, we're not going to have the equations in any particular form. This first equation, it's similar to slope-intercept, but it's not quite there. And then the second equation is in standard form. How you choose to graph these equations is up to you. But I'll discuss why I am choosing a particular method. So with this first equation, we have y equal to 2 minus x. This is not slope-intercept, but it is similar. So I'm going to go ahead and convert this first equation to slope-intercept form by changing the order of these two terms. So we have y equal to, instead of 2 minus x, we're going to have negative x plus 2. This is now in slope-intercept form. So the y-intercept is equal to 2. That means we have the point 0, 2 on this line. And then our slope is equal to negative 1. So we can rewrite this as negative 1 over 1, which means we're going to go down 1 and to the right 1 from that y-intercept. So down 1 to the right 1. And we can repeat that, down 1 to the right 1. Or we can write this slope as a positive 1 over a negative 1. This means we're going to go up 1 and to the left 1. Again, starting at that y-intercept, we're going to go up 1 to the left 1. One more time, up 1 to the left 1. Connecting these points, we get our line. Now with this second equation, this is in standard form. And there's a few different ways that we can graph an equation written in standard form. One way is to convert it to slope-intercept form, and then find both the slope and the y-intercept to graph the line, like we did with the first equation. Another way is to find out where this line crosses both the x and y-intercept. And I will typically use this method if I notice that this constant here by itself, so here the number 4, if that constant is divisible by both of the coefficients, I'll often find both the x and y-intercept. So if we have this equation, 2x plus 2y equal to 4, if I set x equal to 0, that means we're going to get 2 times 0 plus 2y equal to 4. So this first term goes away because 2 times 0 is 0. Now we have 2y equal to 4. And then dividing both sides by 2, we get y equal to 2. So we have the point 0, 2. That is our y-intercept. It looks like a point that these two equations have in common. Well, now let's find the x-intercept. So to find that, we're going to set y equal to 0. So if we set y equals 0, we get 2x plus 2 times 0 equal to 4. So now we have 2x equal to 4. our x is equal to 2. So we also have the point 2, 0. And that's another point they have in common. So drawing this line, we get the same graph. So these two equations represent the same line. Every point that's on the first line will also be on the second line. If we rewrote the first line in standard form, this is x plus y equal to 2, and then multiplied this equation by 2, we would end up with 2x plus 2y equal to 4. So the second equation is simply the first equation multiplied by 2. So therefore, this system is dependent. Now, did we have a solution? Well, yes. We had many solutions. We had infinitely many solutions. Every point that's on these lines is a solution. So all of these infinite number of ordered pairs along this line, along both these lines, is a solution to this system. So we have infinitely many solutions. And since we do have a solution, this system is consistent. Let's look at a second system of linear equations. Again, we're going to solve it by graphing, and then we'll classify the system as either consistent or inconsistent, and as either dependent or independent. So we have two linear equations. The first one's written in standard form. So like I said earlier, when I have an equation in standard form, I will typically graph this by finding both the x and y intercept. If this constant that's by itself, so in this case the 8, is divisible by both of the coefficients. Well, 8 is divisible by 2, but not by 5. That's going to end up with a fraction for an intercept. And that may affect the accuracy of our graphing since we are doing this by hand. So in this case, I'm going to go ahead and convert this to slope-intercept form. So we have 5x plus 2y equal to 8. So we're going to isolate that y. So we have 2y equal to negative 5x plus 8. And then dividing everything by 2, we get y equal to negative 5 halves x plus 4. So b, our y-intercept, is equal to 4. So we have the ordered pair 0, 4 on this graph. And our slope is equal to negative 5 halves. And we can write this as negative 5 over 2, meaning we're going to go down 5 and then to the right 2. So down 5 to the right 2. Now normally I like to do at least one more point, but I'm going to fall off my graph. So we'll stop at just these 2 points. In order to draw a line, all you need is 2 points. So let's go ahead and connect those 2 points to draw our line. Now with this second equation, we have y equal to negative 1. There's no x term here. So that means regardless of our x input, the only value we're going to have for y is negative 1. So when we see something like y equal to a number, so in this case negative 1, this is a horizontal line. All the y values are going to be negative 1. So drawing that horizontal line, we end up with our solution, which is where these two lines intersect or cross each other. And they cross at the point 2, negative 1. Let's go ahead and check this answer. So we check it by plugging this value into both equations. So for the first equation, we're going to have 5 times 2 plus 2 times negative 1 equal to 8. So this is 10 minus 2 equal to 8. So we end up with 8 equal to 8. Well, that's a true statement. And for the second equation, again, we don't have an x value, but we do have a y. So wherever there's a y, we're going to plug in a negative 1. We have negative 1 equal to negative 1. That is also a true statement. So the solution to this system is 2, negative 1. So we have a solution. So this system is consistent. And these two equations do not represent the same line, so this system is independent. A great way to learn is practice on your own. We will discuss in a bit, but go ahead and pause your screen and do these two problems. So for this first system, the first equation is in standard form. I went ahead and graphed this by finding both the x and y intercept. So setting x equal to 0, this first term goes away. We end up with negative y equal to 4, so y is equal to negative 4. Setting y equal to 0, we get 2x equal to 4, so x is equal to 2. So now we have an x-intercept of 2 and a y-intercept of negative 4. You can draw that line. With this second equation, we have x equal to 3. So that means regardless of what y is, the x value will always be 3. So this is a vertical line at x equal to 3. These two lines cross at the ordered pair 3, 2. So this system does have a solution, so it's consistent. And the equations represent unique lines, so it's independent. It's always a good idea to check your answer by plugging that solution back into both equations. You should get a true statement for both equations. With this second problem, I went ahead and graphed the first equation by finding both the x and y intercepts. This resulted in an x-intercept of 1 and a y-intercept of 2. Connecting those points, we get our line. For the second equation, I graphed this by rewriting this in slope-intercept form. We have a y-intercept of negative 4 and a slope of negative 2, resulting in this second line. These two lines are parallel. I went ahead and confirmed that these two lines are parallel by rewriting this first equation also in slope-intercept form. So these two lines do have the same slope. We have a slope of negative 2, but they have a different y-intercept. And parallel lines have the same slopes and different y-intercepts. So we have no solution in this example. So therefore the system is inconsistent and independent. Drop any questions you have in the comments. Continue practicing solving systems of equations by graphing, and I'll see you in the next video.